Okay, well, this is part 2 of a 5-part series looking at supercell formation and tornado genesis of 2 different types, one with supercell mesocyclones and then the other one non-mesocyclonic tornado genesis, and that's what I'm going to focus on in this part. Okay, so our objectives with this lesson would be to identify the main ingredients associated with tornado genesis, which interestingly don't really vary. It's just a source for stretching and vertical vorticity, and then look at the key physical features that are related to non-mesocyclone tornado development. Okay, so tornado genesis, of course I'm cheating here. We show a picture of actually supercell tornado. This is the start of the El Reno tornado. Point is, whether it's a tornado like this, or one that looks like this, much more typical so-called land spout look, the basics of tornado genesis are the same. It's just a matter of how you get the ingredients arranged. We need near surface vorticity, and simply put, a swirly or spin. You need something near at the ground where there's spin, and you need something to stretch that. Now, this is the scary part if you are an operational meteorologist, or even if you storm chase or anything else. How many different types of surface-based thunderstorms cannot possibly have some sort of low-level spin and updraft stretching? Good luck if you think there's any of them. And anyone who watches convection along the Gulf Coast, or say the Florida sea breezes even in the summer, and you wonder, why was there a random tornado or two today? Eventually you co-locate some sort of swirly with an updraft. And you see this all the time down by the Florida Keys or in northeast Colorado, where there's something in the background, confluence lines with the islands based on the background flow, or terrain-driven circulations that provide the circulation. And anytime you get updrafts on top of these swirlies, you can get these non-mesocyclone tornadoes. Now, supercells, they just provide the vorticity a different way, and it's a more repeatable process, and it's more internal to the storm, and we'll talk about that more in part 3. Well, guess what? We had developing thunderstorms. I assume you would figure that out, or I wouldn't show you this case where nothing happened. Here's one. This is just to the south of Wichita. You see, and to the upper right, there's a band of convection, and off to its immediate southeast is the outflow boundary with the convection, and then that north-south line is actually the front that's been enhanced. You're looking at insects or something along the boundary, and that little intersection is about where the arrow points. This is where the outflow from the existing convection intersects the front, which had a lot of vertical vorticity along it. So what we notice is that as we go forward, there's a tendency for new reflectivity formation in the direction of the intersection, because the outflow that extends to the south of the storms is moving south. So that intersection point is propagating southward with time. We get new development. Aloft, the reflectivity increases, and you even see the small weak echo region. So that's a sign of locally a very strong updraft sitting right atop that boundary intersection. So in the low levels, this is just the base velocity from, and the radar site is directly to the north. So if you look where the arrow is, there's weak cyclonic shear, just weak inbounds to the east and weak outbounds to the west. Nothing very strong, but we go forward and you see a stronger circulation signature in the low levels becomes apparent. And if we look aloft, initially it was just convergent there, and now we see cyclonic, and then you see actually quite a strong circulation that develops from the bottom up, which is typical of non-mesocyclone tornado genesis. And this is actually the tornado that was produced. And the one thing that I like to emphasize in this case is you notice temperatures were in the 80s, dew points were near or above 70. Non-mesocyclone tornadoes don't have to look like little dirt whirlies. That's not always what they look like. This actually produced EF2 damage, and unfortunately it sat over a farm for about 15 minutes, and eventually the damage added up. So this is one of those things, and I will be honest, this was a case where I put out a severe thunderstorm watch early in an evening shift and perhaps did not give the environment enough credit. So this was a strong tornado in a severe thunderstorm watch that I issued. There were some wind and hail reports, but it just goes to show that there are plenty of things you need to consider when you're trying to forecast this. Because if you come in with a preconceived notion of what you think the outcome's going to be and you ignore the actual environmental evidence, you can be left holding the bag. So the point is, I've been doing this for a long time. It happens to the most experienced forecasters, but there are ways to sniff out these events. And this is actually a fairly repeatable pattern that you will see, especially in the central United States. In certain years, you may see it 2 or 3 times in the warm season.
Welcome to the visit training session. We're going to talk today about total lightning and how it may be related to non-supercell tornadoes. I'm Ed Zoke, and we'll begin with the next slide. Okay, so here's an overview. Total lightning has become more widely available in the last few years, in part as we get ready for GOES-R. And there's been a lot of research done, especially by the folks down in NASA Sport in Huntsville, Alabama. And this module, again, will examine total lightning and its possible relationship to non-supercell tornadoes and only non-supercell tornadoes. So we're not talking about hail or supercell tornadoes here. And we emphasize the results are preliminary. And that's why we kind of had a question mark in the title. And we need more cases. So we welcome any input from those of you out there who may see a non-supercell tornado and have some input for us. Okay, so here's how we'll structure this today. We'll have a little introduction about total lightning and then a little review about non-supercell tornadoes. Then we have a very detailed case, this tornado that went right over DIA, Denver International Airport, on the 18th of June in 2013. And then a case not as much detail, but it'll give you an idea what the total lightning data would look like in AWIPS, and then how we might apply these ideas to warning operations. All right, so a brief review. What is total lightning? It is the combination of cloud-to-ground lightning, which you've had on AWIPS for many years, and then in-cloud lightning. So until recently, in-cloud lightning was only available through these special lightning mapping arrays, and Sport had one of these in Huntsville, Alabama, probably one of the earliest arrays. So that's where a lot of the research initially was done. In the last year or so, since 2014, total lightning has also been available through Earth networks to the National Weather Service and via AWIPS now in most places. In the future, and this is the connection to GOES-R, total lightning will also be available from the Global Lightning Mapper on GOES-R. So I borrowed a few figures from some sport-related training material, and here's one of them here. You can see in the the regular flash, if you had just a cloud-to-ground detection system, you just have this one point, but with the total lightning, these are all sources in that one flash, and that's what we can measure with these LMAs. Now here's a case put together by Rob Cox. He presented it at the 2014 High Plains Weather Conference. It occurred about a month after the Denver tornado, in this case only 10 miles northwest of Cheyenne. And he again was able to use the Colorado Lightning Mapping Array, which extends into southeast Wyoming. And here's a nice picture of the tornado from the MIC at the time, taken around 0Z on the 30th or at 6 p.m. on the 29th of July. And that picture was, again, the tornado about 10 miles from Cheyenne, and this is how the photographer was looking off to the northwest at that picture. So Rob kind of schematically noted this here. This boundary was initially here. We had then the outflow coming from these cells here, and there was earlier outflow from these weak storms to the west. And this is how it looked in terms of velocity about 15 minutes prior to the tornado. Now we went and looked at this very closely with Rob and thought that being so close to the radar, we'd probably be able to construct these time height cross-sections again, but we never really saw a very good coherent signal and velocity for this case. We do certainly have nice growth of a cell that we could have certainly had a nice time height cross-section of the reflectivity, and here you see the view at 6.4 degrees, which isn't all that high in the storm since we're so close to the radar. Pretty strong reflectivity, getting up above 60 dBz. Right. And this is about the best we saw maybe in terms of a rotational signature, and it isn't all that great. And we certainly did not see any coherent signature as we looked up and down in the vertical or with time. So this is kind of interesting. We're only 10 miles from the radar in this particular non-supercell tornado was much more difficult to see than the Denver one. Okay, so now, since we're not able to do those time-height cross-sections, what we're going to do is show you sort of a pseudo GLM display. In other words, what you'd see with the global lightning mapper, but constructed from this ground-based network. And this is through Sport. This is a display that Sport has worked out. Note first that we are very zoomed up here. These are some of the streets in the Cheyenne area. There's I-25 over here, and so this is a very zoomed-in image. The distances are quite small. So what we have, of course, as I mentioned earlier, instead of source density, you would have flash density, but the idea would be the same. So now as we step ahead, watch this one area right in here, and you'll see an increase. We're now at 2351. The tornado is around 0Z, so in about 9 minutes. And watch this. Every 1 minute again, we will have that kind of density. There was that initial peak, and then it slowed down, and then another rapid jump in here. And again, these are quite close. You could almost think of this as one area, but there is a really nice increase here about 5 minutes before the tornado, and then that continues, and then it actually shifts a little bit, and then goes away as we actually get into the tornado time itself. So Rob's conclusion, I'll go ahead and just animate this here. Rob's conclusion, he felt that there was kind of a nice little signal about 5 to 10 minutes before the tornado for this particular case. Right, so again, the summary for the Wyoming case, again, like we saw in Colorado, and as you probably see in most non-supercell cases, there was a pre-existing low-level boundary, there were steep lapse rates, so you get a good updraft, and maybe about 10 minutes before the tornado, there was this lightning jump. And then kind of importantly, and emphasizing how hard it can be to forecast these from just radar data, although we were only 10 miles away, we didn't see a very reliable sign of a circulation in this case.